We present our final project for the ME231 class. The title is Target Tracking Cluttered Environments with the Quadcopter. The authors are Carlo Bosio, Fiona Kopp, Tia Young. Okay, so the goal of the project is to be able to track a three-dimensional trajectory with a quadcopter, and this can have several applications like catching falling objects or docking in moving vehicles with drones. There are many problems related to this project, like the fact that the drone is highly nonlinear and is naturally unstable, and the obstacles and the clutter make the problem non-convex also, as well as the nonlinearity.
So for this project, we have two drones, UAV A and UAV B, in a constrained cluttered environment. UAV A is the one that we are tracking with UAV B, and so we made several assumptions so that we could simplify this problem down a little bit more. For example, we assume that UAV B has the full history of positions of UAV A to aid with the reference tracking. We assume that we have a perfect model with no external disturbances, and that we know the environment and all physical constraints in the environment fully. We used a non-linear dynamics model in 12 dimensions, but simplified down the tracking problem to only include 3 dimensions of position. We implemented this not in real time, but just in simulation. So here's the 12-dimensional state vector, as well as the 4-dimensional input vector, which is the propeller forces on all 4 propellers. And then on the bottom of the slide is the mixer for using this as the input vector. And this slide shows the nonlinear dynamics model, which we used. Another option could have been for us to linearize this every n time steps, but we decided we were interested in exploring the nonlinear dynamics and how it affected the problem.
So our problem is highly constrained. We inserted several types of constraint in the problem. The first one is a bounding box, that is a feasible 3D area where the drones are allowed to go. We inserted cylindrical obstacles, a bunch of cylindrical obstacles, which are nonlinear constraints because they depend on the square of the position variables. And also we try to improve the persistent feasibility properties of this problem by using the Big M technique, which is detailed a little better in the report.
So for the tracking problem, one approach would be to track the current position of the target UAV, but another option would be, since we have the history of the previous positions of UAV A, we can predict potentially or use different prediction methods to generate an estimate of a future location and track that estimated future location. So there's different possible strategies for this position forecast, including linear feed forward through the dynamics by assuming constant velocity. So this was implemented in some of our results in comparison to tracking just the current position. Other potential strategies that could be further investigated include assuming constant curvature or constant acceleration and curve fitting a higher order polynomial, such as a second order polynomial, or looking into using an extended or unscented Kalman filter.
So how do we generate the trajectory of drone A? So the target drone, we just run a CFTOC with a horizon of 500. Of course, the CFTOC is feasible to try to reach a specified location, which in this case is 10, 10, 5 in 3D space. So the trajectory is pre-generated, and then it's fed in the pipeline to generate the trajectory of the chasing drone, which will have knowledge about the previous positions and the current position, but of course not the future positions. And the future estimate will be handled with the prediction pipeline. So we formulate the MPC problem as a iterative solution of the CFTOC problem, which you see in the slide. It's a standard tracking problem where X bar is the predicted location of the target UAV, and U bar is computed as the steady state solution of the dynamics using the target UAV position. And then, of course, we use nonlinear dynamics, which is adapted to the discrete model through Euler discretization. There are the initial conditions, state and input bounds, cylindrical obstacles, and the Big M constraints.
So then we experimented with different ways of solving this MPC problem. And for each of these trials, we tried changing the horizon length as well as some state and input constraints. And here are some examples. So in this example, our horizon length is 10, and drone B is given a higher input constraint than drone A. This allows it to have a higher maximum velocity compared to drone A. And also A starts half a second earlier than B. But this problem became infeasible after some time because drone B is colliding into the central pillar. This is due to its short-sightedness. So in experiment 2, we increased the horizon length to 20, and A also starts 1 second earlier than B. But this problem also became infeasible after drone B exceeded drone A in its horizontal position, but it's trying to make a sharp turn in order to collide with drone A, but this is not allowed due to the Euler angle constraints. So we suspect that a new policy needs to be introduced after this point to allow it to complete this sharp turn. So for future work, we would continue to explore the trade-off between this persistent feasibility problem and the state constraints, as well as introducing a new policy to complete the chase. And in order to reduce some computation time, we would consider linearizing about every time step or every few time steps instead of using the nonlinear model. And we would also improve the prediction strategy for drone A, as well as look into the optimization-based collision avoidance problem, as well as the reference governor techniques.